we have looked at temperature and temperature scales. So now we want to see what happens when temperature changes. One thing that happens is something called thermal expansion. Thermal expansion is exactly what it sounds like. When things get hotter, they expand. So the big thing we're talking about with this, we're going to look at thermal expansion first with solids and liquids. With gases, things behave just a little bit differently, but solids and liquids, that's its own category. The difference we said between a liquid and a gas was whether or not this thing had a constant volume. A liquid in general has a constant volume, but when you take that liquid and then you heat it up, that volume changes. So first I'm going to look at solids and at a length expansion. If I've got a bar like this with a length of L, we'll call this thing L initial. And this thing sits at some initial temperature. If I heat this up, so if I put maybe some flames underneath and heat this up, what's going to happen, this bar is going to get just a little bit longer. I'm going to say let's pretend that the left side is attached to a wall or something so that we can't expand in that direction. This bar is going to get just a little bit longer, and I'm going to call that distance, that difference, change in length. There is a simple equation that relates these, and it looks like this. The change in length is equal to alpha times L times the change in temperature. The change in temperature, this is one of those spots where it doesn't matter if we are using degrees Celsius or Kelvin because they have the same step. L, this is the initial length, and then alpha, this thing, is called a coefficient of linear expansion. That coefficient of linear expansion is going to be different for different materials. So if we have like aluminum has a coefficient of expansion of 25 times 10 to the negative 6th, and the units on this thing are kind of weird. They are degrees Celsius to the -1. The reason they're that, we need a final answer that's in meters. We've got this initial length that's in meters, and a change in temperature that's in degrees Celsius or Kelvin. So this thing must have units of 1 over degrees Celsius, or 1 over Kelvin, if you like. So aluminum's got this 25 times 10 to the negative 6th inverse degrees Celsius. I'm just going to give you a couple of them to work with. Gold is 14 times 10 to the -6th inverse degrees Celsius. What other ones would be good? We can look at like regular glass. And glass can be a whole lot of different things, right? You can make glass a lot of different ways, but 10 times 10 to the -6th inverse degrees Celsius is a pretty representative number. We can also do this with liquids. So let's not worry too much about liquids for linear expansion. That doesn't make much sense, but we don't have to stick to linear expansion. We can also do area, and we can also do volume. If we are looking at a solid plate, like this maybe, and this has some initial area, and we heat this thing up, then this thing is going to get just a little bit bigger. Right, we're going to get this little increase in area. And we get a formula here that says that our change in area is equal to 2 alpha times the initial area times change in temperature. So it works a whole lot like our change in length. Our change in length was equal to just alpha times a sub I times delta t. And our change in volume, while we're at it, is actually going to be about 3 alpha. This was an initial length. Our change in volume is going to be about 3 alpha times initial volume times change in T. However, change in volume is something that we can apply to a liquid also, and we can't really do a linear to a liquid. So instead, we give this a different value, beta, but for a solid, beta is approximately equal to 3 alpha. So it works out the same way. So I would like to give you a couple of these beta values also. We might have, let's say, ether, like a diethyl ether sort of thing. Ether has a beta value of 1650 times 10 to the minus 6th. And that is still degrees Celsius inverse. Other ones that might be helpful, mercury. We get a beta value of 180 times 10 to the minus 6th. And water, because why not? Water gets 210. If you think a little bit about how this works into the equation, you will get kind of a feel for what's going on. A high value of beta, for example, when we're talking about liquids, a high value of beta means that it takes a lot more energy to get that to expand. A low beta means that with the same temperature change, or right here, that with the same temperature change, you're going to get a relatively large increase in volume. I'm going to go back and fill these out, the aluminum, gold, and glass, so that you can kind of get a feel for that too. Beta for aluminum is about 75 times 10 to the minus 6th inverse degrees Celsius, which is about times 3. That one's actually just about exactly times 3. For gold, we get 42. Again, times 3. And for glass, we get 27. Now I'm giving you these numbers to not a whole lot of significant figures, although you don't usually see those to a whole lot of significant figures. But if you did these out to more, this might be a, I don't know, a 74.85 or something like that versus 75. So it's going to vary a little bit, be a little bit off from being triple, but it's really close. That's thermal expansion of solids up here above this line, solids, which we can do linear or area based, which is just 2 alpha, or volumetric, and then same thing with liquids, except we don't do the linear and area there, we just do the volumetric.